Have you ever stopped and really wondered what's happening deep down inside your computer when you run a program? I'm not talking about theory. Today, we're going on a live, hands-on journey right into the heart of the CPU itself to watch code run one single instruction at a time.
Yep, that's the mission today. No more abstract diagrams, no more just waving our hands and talking about concepts. We are going to get our hands dirty. We're going to watch a real process execute on a real computer and see exactly what's going on inside the machine.
Okay, so think of it like this. Anybody can drive a car, right? But it's a totally different experience to pop the hood while the engine's running and actually see the pistons fire and the gears turn. Well, that's exactly what we're doing today. Our engine is a computer process, and we're about to see every single move it makes. Let's dive in.
So our lab for this whole experiment is this trusty little Raspberry Pi running Linux. And what's super interesting here is the CPU architecture. It's ARM. This isn't your typical Intel chip. And that means its native language, the actual machine code, is completely different. It's a great little reminder that the code for your phone, which probably has an ARM chip, can't just run on your laptop without being retranslated. It's true. Different computers really do speak different languages.
Now, to see what's happening with total clarity, we need a really simple test subject. We're not going to fire up some complex app. Nope. We're going to use this tiny little program written in C that just does a couple of basic things. And that simplicity, that's our superpower here, because it's going to let us see every single step without getting lost in the noise.
So here it is. This is our entire recipe. First, we just create two numbers, 1 and 2. Easy enough. Then we add them together. After that, we print the result to the screen so we can see it. Then, just for fun, we add one more to the total. And finally, we just tell the computer, hey, we're done, and everything went great. That's it. 5 simple steps from beginning to end.
Right, so the thing is, the computer can't just run that C code directly. The first step is to translate it into a language called assembly. This is kind of the halfway point between our human-readable code and the pure ones and zeros the CPU actually gets. You can see our simple C equals A plus B becomes a very specific, kind of cryptic instruction. It's like translating make a sandwich into pick up bread, open jar, scoop peanut butter. We're going to see how the processor handles these nitty-gritty steps in just a minute.
Okay, but before we create that final runnable program, we add one absolutely critical ingredient: debugging symbols. Seriously, think of this as creating a super detailed map. This map connects every single low-level machine instruction all the way back to the original line of C code that it came from. Without this map, we'd just be staring at a sea of numbers, completely lost. With it, we can actually navigate.
All right, so we have our program, it's compiled, it's got our map, so why don't we just run it and watch? Well, there's a pretty big problem. It is just too fast, like impossibly fast.
I mean, our entire program, from start to finish, runs in less than 1 millisecond. That's faster than a lightning bolt. If you tried to look for it in your list of running processes, it's born, it does its job, and it's gone before your screen even has a chance to refresh. It's literally like trying to take a picture of a ghost.
So, how in the world do we solve this problem of insane speed? We need a way to freeze time. And for that, we have an amazing tool called GDB, the GNU debugger. This tool is what gives us the superpower to take control of our program's execution.
Honestly, the best way to think about GDB is as a remote control for your code. It lets us start the program, but then immediately hit pause. It lets us play just one single instruction at a time and then pause again. It is the ultimate slow-motion camera for software, and it lets us examine every single frame.
Okay, this is it. This is the moment we've been building up to. We've loaded our little program into our special remote-controlled GDB. We're about to press start and then pause almost instantly. We are now officially going live inside the CPU to watch our program run one tiny step at a time.
Now, as we're looking inside, we need to keep our eyes on 2 key players. First, there's the program counter. Think of it like the foreman on a construction site, always pointing its finger at the very next instruction on the blueprint. Second, you've got the registers. This is the foreman's workbench, a small set of super fast internal scratch pads where all the actual math and work gets done.
And here we are. We're in. Our program is running, but it's frozen in time. The program counter, our foreman, is pointing directly at the instruction for C equals A plus B. The numbers 1 and 2, they're loaded up and ready on the workbench. The CPU is just waiting for the signal to do the math. All right, let's hit next and see what happens.
Wow, look at that. Did you see it? The program counter jumped forward from one memory address to the next. It's now pointing at the next job to do. But here's the magic. Look at the register called R3. A second ago, it held some random value. Now, it holds the number 3. The CPU literally just performed 1 plus 2 and put the result right there on its workbench. We just saw it happen.
That was awesome. Okay, let's keep this going. The very next instruction in our code is to add 1 to our result. The program counter is pointing at it right now. Let's press Next one more time and keep an eye on that workbench.
And there it is. Bam! The program counter moved again, getting ready for the next thing. But look at register R3. It was 3, and now it's a 4. We just watched the CPU execute the command to add 1. This isn't a simulation. This isn't an animation. What you're seeing is a snapshot of the actual state of the processor's brain, frozen in that exact moment in time.
Let's just pause and recap what we just did because it's pretty incredible. We took a simple C program, we translated it, and we used a debugger to basically stop time. We walked through it instruction by instruction, and we saw the two most important parts of the CPU, the program counter and the registers, change in real time. We just bridged that huge gap between code on a screen and what a machine actually does.
And you know the coolest part about all of this? This isn't some secret technique that only experts know about. This is not magic. It's a fundamental skill, and it's something that you can do right now on pretty much any computer out there. Now, as you explore, I promise you, you're going to find little mysteries. Even while doing this demo, I saw a few small surprises. That's completely normal. Real systems are complex. And every one of those little mysteries isn't a bug. It's an invitation to dig just a little bit deeper and understand a little bit more.
So if you want to try this yourself, here is the dead simple recipe. Write a tiny C program. Compile it with that special -G flag to add your map, then start GDB, and inside just type start. That's it, you're paused. Then you can use info registers to look around and N to take one step forward. It's that easy.
And that's really the crucial point of all this. You don't need to memorize every single register name or understand every line of assembly code. You just need to see it for yourself, just once. You need to experience that moment where a line of your code becomes a real, physical change inside the CPU. Because once you see that understanding, it changes how you think about what code really is and what it does forever. It totally demystifies the whole process. It's not magic. It's just a series of incredibly fast, simple steps. Which really just leaves us with one last question. Now that you know the secret of how it all really works, what amazing things are you going to build?